So we're going to talk about hexagonal close-pegged structure. Now, what's happening in this instance is that you throw your atoms and they're going to form this thing. So this is layer number 1, layer number 2, layer number 3, layer number 4, layer number 5, so on and so on. What's important to notice is that you can draw a little hexagon like this and have the structure be something like this. So it's going to be a little bit different from what we studied because these are no longer cubes. They are basically hexagonal prisms that are going to be the repeating unit, right, or the unit cell. So you can extract all of these atoms and you're going to see something like this, which is very beautiful. So you're going to see that you have 6 atoms surrounding this. You have 3 atoms in the middle. You have 6 atoms at the bottom. So 1 atom is in the center like this, surrounded by 6 atoms, forming a hexagon. The same is happening, and 3 atoms are inside of this unit structure. These atoms are not touching because there are 3 atoms in the middle. Okay, so it's important for you to see that these 2 atoms are touching. So from this center to one center, this is going to be R, 1 radius. This is going to be R, so it's going to be 2R. And you can see that this atom also in the center, like this atom over here, is touching this other atom here. So if you're going from this center, this is going to be R. If you go from this center to the center of this other atom, it's also going to be a radius. So you can see that to go from this corner through to the center of these atoms in the middle is going to be 2R. The same as going from one atom in this corner to this other atom is going to be 2R. So keep that in mind. We're going to come back to this. So it's possible for us to like shrink these atoms down so that we can really see the hexagonal structure that we're going to form. And we can see that this hexagonal structure is the unit cell. And we can do that by looking at this structure over here. So this is basically the structure that we're going to form. So this is hexagonal. Basically, this is something that you're going to notice. So if you look at it very carefully, you have 6 atoms again forming the outer hexagonal and 1 atom in the middle. And then you also have 6 atoms at the bottom, 1 atom in the middle, and these 3 atoms are inside. Remember that this is like the center connected to the other center. So this is 2R, this side of this hexagonal structure. And if you were to look at this side again of this hexagonal structure 2R, and from this center to this other center is also 2R, like I've described in the last part. So you can see that we have 3 atoms inside. One interesting thing about this is if you were to look at it from top down, shift it like this, look at it from the top. So I'm looking at it from the top. You can see that if you were to draw a triangle with these 3 atoms, like one atom is going to be in the middle. It's going to be directly aligned. It's below it, like it's below it, but it's aligned with the center of this triangle. And if you were to draw another triangle, so if you were to draw another triangle like this, one of these atoms is going to be in the center, another triangle, one of these atoms is going to be directly in the center of this equilateral triangle, right? If you were to divide hexagonal with equal sides, it's going to form equilateral triangles all out. Okay, so it's very important for you to just be thinking about this structure when we'll be doing this specific model. So it's important now to realize that these hexagons are the ones that are just going to repeat, right? So there's going to be another hexagon on top, another hexagon on the side. So if you're extracting this hexagon as the unit cell, these atoms are going to be sliced 6 ways. So this atom is going to be sliced 6 ways. I'm going to explain how that comes about. This atom is going to be sliced in half. So the other half will belong to the other hexagon by this line over here. And these atoms, these 3 ones, will remain inside the unit cell. So this is going to be useful for you to think about when we're talking about the number of atoms. Okay, so this is what I'm talking about in another different way. So like I said, if you were to draw 3 triangles like this, like so, these atoms are going to be directly aligned with the center of these specific atoms. And this is what we call the unit cell for a HCP, so hexagonal close-packed HCP. And it's basically like this. It's basically a hexagon. It's no longer a cube that we were typically used to. So typically we're seeing cubes being our unit cells. In this case, it's now a hexagon. Okay, so the actual structure, that's when you're going to have atoms at this corner, atoms at that corner, like, so this is what your exam sketch will be like. And 1 atom in the center, atoms at these corners, atom at these corners, 1 atom in the center, very big atom, and then 3 atoms in the middle. Okay, so 3 atoms like in the middle, something like that. Okay, so this is like basically what you'd be saying, right? Atoms at the corners, atoms on top and bottom, and 3 atoms in the center. So similar, we're going to define lattice parameters as always. So lattice parameters are basically the dimensions of the unit cell that you have. For our cube, this was basically A, which was a bit straightforward. This was basically A. But for hexagon, the side of one of these hexagons is going to be the lattice parameter A. Remember, a lattice parameter is just a value that we're just thinking about, right? It's just a way of describing the lattice, right? So this is going to be A, and this is going to be C. The height, basically, of this hexagonal structure is going to be C. So we have two lattice parameters, parameter C, which you didn't have before for a cube, because a cube is just A throughout. So we have the height C of this sketch, and we also have A, which we're supposed to find out later, as always. So that's important for you to think about. The next aspect is the number of atoms. You might be asking me, well, what is the number of atoms in HCP? Which is a very important question to ask. So the first thing that we're going to realize is we have 3 atoms in the center, which is very important. Atom number 1 over here, atom number 2, and atom number 3. So you have 3 atoms within the center. So it's going to be 3 plus, and you're slicing this up. So you're slicing this up to create the hexagons, right? So if you were to do that, if you were to slice this across that plane, you're going to slice it and you're going to be left with this, right? So I've let the center atom be red so that it's easier to visualize. So you can see that 1/2 of this center atom is going to go away, okay? So only 1/2 is going to remain in this plane, right? So there's going to be 3 atoms in the middle, and 1/2 of this big fella that remains inside. The other half goes to the other, like, hexagon that will be above, okay? And then another half is going to belong to this fella. So we're going to have 1 atom basically coming from the center atoms. So 1/2 of an atom, and then 1/2 of an atom. And it's important for us to study what's happening at these corners, right? So we have 6 atoms on top, 6 atoms on the bottom. So we have 12 atoms in total. 12 atoms in total at corners. So 12 atoms that are in corners at total. And then if you analyze one atom, so if you're basically going to analyze this atom, remember it's going to be sliced in half like this, okay? So if sliced in half, this is what you're going to have. But you can see that if you're to draw a line going down like this, not all of this atom is going to be inside this unit cell. So you've already removed 1/2 of this atom. It's gone. If you're to draw a hexagon, not all of it is going to be inside. There's going to be basically a whole chunk like this that's not going to be inside because it's going to belong to another unit cell. It's very possible for you to draw another cell going in this direction, or to draw another cell basically starting in this direction. So this can be one other, like this can belong to one other hexagon. This other side can belong to another hexagon. This can belong to another hexagon. So you can see that we can divide this 3 ways. Okay, this atom can be divided 3 ways, and only 1/3 of that half is inside the cell, right? The other one belongs to another hexagon. The other one belongs to another hexagon. So you can see that we have 3 pieces. Only one belongs to this hexagon. So first up, we had a half that was removed, and we removed 1, 2, 2/3. So we only left with 1 over there, right? So you can easily see that this is 1/6 of an atom that remains, right? Because like 2 of these are gone, and the half had 3 that it could form. So 3 plus 1, 2, so 5/6 is removed entirely. So only 1/6 of the atom remains inside. I hope that makes sense, sort of. So that means 1/6 of an atom is found at every corner. 1/6 of an atom, 1/6 of an atom, 1/6 of an atom. So in total, you have 1/6 of 6 atoms. So at the top, you have 1/6 of 6 atoms. At the bottom, you have 1/6 of 6 atoms. So in total, it's 1/6 of 12 atoms, which is going to be 2 atoms due to the corners. So it's going to be plus 1/6 by 12. So that's going to be 3 plus 1 plus 2. So you're going to have 6 atoms. Okay, so you have 6 atoms inside of um this unit cell. The next thing that you're going to ask me, which we always talk about, is going to be the relationship between lattice parameters and the radius. So the next logical thing is going to be the relationship between lattice parameters A and C and the value of R. So this is going to be like the next logical relationship that we're going to talk about. Okay. So for this one, I need you guys to pay a little bit of attention. It's a little bit tricky than you would anticipate. So the first thing that we're going to talk about is A. We can easily see that A is equal to 2R. Why? Because if you come here and if you look at this here, you can see that these two centers are joined, and the distance between those centers is basically the length of the side of your hexagon. And you can see that it's connecting one center to the other. So 2R is going to be the value of A. So we're done, right? Not quite, because we don't have the value of C, right? We don't know what C actually is. For A, it was quite straightforward, right? If you were to draw a hexagon like this, and I said that one atom is this big, the other atom is this big, the other atom is this big, you can easily see that, okay, this is like half, this is like R, this is like R, so 2R is equals to A. And it's A throughout, so A here, A here, A here, A here. So this was easy. But the problem is we don't know what the height is, how long the height is. So that's a bit of a challenge. And we're going to talk about how to calculate that. I want you to realize something very important, effect that I'm going to talk about, what I mentioned. If you were to look at your triangle from the top, so let me remove all of that. If you were to look at it from the top, right, like if you're looking down, this atom in the next plane, which is just in the center, like this whole plane is in the center of this height, is going to be directly in the middle. Like it's going to be aligned with the middle of your equilateral triangle that is made by these 3 atoms, right? Visually think about it. This atom is going to be directly in the center, which I've talked about, right? It's going to be directly in the center of this specific equilateral. So if you're to move from this corner, so let me label these atoms. Let's say this is A, this is B, and this is C. So if you're to move from B towards the center, so from B towards the center of your equilateral, so let me make this, okay, I'm going to call that distance x, right? So the distance from one corner atom towards the center. You can do this at any point. You can even do it at this, right? The distance from this corner atom towards the center can still be x. It doesn't matter where you do it. Okay. And if you're to move down like this, right? Be in mind that this is like C. From this point to this, it's C. So the center plane is in the middle, right? It's in the middle of C. So it's going to be C over 2. From this point to this point, it's going to be C over 2, right? Because the center plane, like this plane, is in the middle of these two guys, okay? Shouldn't be too complicated. It's in the middle of these two guys, so it's going to be at C over 2. Okay, so this height is going to be C over 2. And you can see that if this is X, this is the same, because like from here to here is the same from here to here. So this is also going to be C over 2. Okay, so it's a little bit complicated. Okay, C over 2. So this is like a little triangle. You've gone from this to the center, you've gone down, so you can complete your triangle and come back to B. And we're going to call this Y. Yeah, so we've just created a little nice triangle over there, right? And you can even see it with this atom, right? We're saying this is our center. If you have something like this, if you have something like this, connecting those 3 atoms together, we're just saying you're coming from this center over here. So you're going from this atom over here, right through the center, going down and then coming back up. So that's the triangle that you're creating. Okay, so if I were to do that, I'm going to create a triangle that I'm going to extract. Okay, so just to make sure we're all on the same page, I'm going to draw it again. So basically, if you were to connect this, this is going to be in the center, and this is X. Okay, so if we're going to extract this triangle, so if we were to view it just from the top, like a little bit differently, like this, and if we were to extract this triangle that we've talked about, which is this triangle with X, Y, and C over 2, you're going to see that it's a right angle triangle, sorry, which is something like this. Okay. So this is going to be X, This is going to be c over 2. This is going to be y. And this is going to be how we're going to find the value of c. Okay. Now, the first thing that we're going to do is realize that we don't necessarily know the value of x. So x is the value that we're going to take, which is going from the center of an equilateral to one of the vertices. Okay, so that will help us find the value of x. And y is very straightforward because y is from the center of a corner atom to the middle atom, which is over here. And you can see that if you're going from the center of a corner atom to the middle of the middle atom, is going to be 2r, like we talked about, right? Because these atoms are touching each other. So to go from the center of one atom to the center of the atom in the middle plane, they're like really touching each other. So it's just going to be 2r. Okay. So with y, we're done, right? We already know that y is equal to 2r because we're going from the center of the atom at the top to the center of the atom at the bottom. But we don't know is the value of this x over here. Okay, so if you want to find the value of x, it's important for you to realize that, wait, you're looking at an equilateral triangle. So for the value of x, it's important for you to realize that you're looking at an equilateral triangle. This is your center over here, center coordinate. So I'm going to call this center coordinate C. Okay, so this is the center C1, for example, and you're trying to go from B. So the value of x is basically you trying to go from B towards the center over here. Okay, now it's important for you to realize that we can actually use geometry to find out this value of x. Which is why I said HCP is a bit complicated, but it's fun. It's not that difficult. Okay, so for a center, I can prove this, but it's complicated and I don't want to do that. If you have three coordinates, x1, y1, x2, y2, x3, y3. If you have three coordinates like this, and if you want to find the value of the center, the centroid for an equilateral, x bar is just going to be the average of all x coordinates. x1 plus x2 plus x3 divided by 3. What is the average value basically? Y bar is just basically going to be y1 plus y2 plus y3 divided by 3. Okay, so if I can say that this is like, I can say y1 and y2 are equal, right? So I can say they're equal to 0, and I'm starting like at 0 at this point. So you can see that if y2 and y1 are 0, y bar, the average value of your y bar is going to be y3, sorry, let me do this, y3 divided by 3. Okay, it's going to be the value of the y value up until b divided by 3. Okay, but you know the height, right? So you know that from these corner atoms, you know that this is A, this is A, this is A, because you're looking at a triangle like this. So it's A here, A here. So it's basically like an equilateral triangle has equal sides, basically. So you can find the value of the height, y3, right? Because y3 is basically like the opposite hypotenuse. So h, which is just y3, is going to be the square root of, using Pythagoras, of this is a, so it's a squared, the hypotenuse, minus this is a over 2. So from this one to this one, that's a over 2. So a over 2 squared. So it's a over 2 here, a over 2 here. Okay, so a over 2 squared. So if you compute this, you're going to get root 3 over 2a. So y3, the height, is going to be root 3 over 2a, and y bar, which is basically the average value, y bar is basically going to be root 3 over 2a divided by 3, right? So times something like this. So this is going to be the average value for your value of y bar. So this is what the average value is gonna be. So you can see that y bar coming from the bottom. So the average value of y is measured from this axis. So you can see that this one is going to be y3 over 3, right? To come from this side, like this baseline, to reach the center, it's going to be y3 over 3, right? Because like we're measuring y3 from this 0 axis over here. So if this is y3 over 3, that means x is going to be what, right? If from this point to this point is going to be 1/3 of y3, x is going to be 2/3 of y3, right? That makes sense, right? So we're measuring relative from this baseline. So x is going to be 2/3 of y3. And I already know what y3 is. It's already root 3 over 2 times a. So I've now found the value of x. Okay, so I have the value of x, I have the value of y, which is 2r, and I know that a is equal to 2r, so y is equal to a. And I can find the value of c over 2. So coming back here now, I can say this is c over 2. So coming back here now, I can say that this is c over 2, and I can say that this is x, which is 2/3 times root 3 over 2, so that's root 3 over 3a, and this is a, basically. So using Pythagoras, which is a very smart way to do things, c over 2 squared will be equal to a squared minus root 3 over 3a squared. Okay, so this is going to be just 2/3 a squared, and c is basically going to be the square root of 2/3 a squared times 2, effectively. So c, if you find that in the calculator, you're going to get 2 root 6 divided by 3 multiplied by a. So yeah, we're done. We found the value of c. So it's a little bit complicated, but that's the whole point of advanced math. It gets a bit tougher to explain these concepts. But once you have the value of c and once you have the value of a, you can basically now find the volume of the unit cell. Bear in mind, why am I doing all this? I want to find the atomic packing factor. That's why I want the relationship between A, C in terms of R. So I want to find the atomic packing factor, APF, which is basically the total volume of atoms divided by the volume of the unit cell. Okay, so you can be like, okay, I get that. So the total volume of atoms, so let's start with VA. So I'm going to call this VA as always, and VC. So the total volume of atoms is going to be equal to, remember I have 6 atoms, times 4 over 3 pi r cubed. Okay, and you can simplify this. This is 8 pi r cubed, and remember that r, if you come here, is a is equal to 2r, right? But a is equal to 2r, so r is equal to a over 2. So this will be 8 pi a over 2 cubed. So it's going to be 8 pi a cubed over 8. So it's going to be pi a cubed. So this is the volume of the atoms inside the unit cell. And if you want to find the volume of the unit cell, and bearing in mind that this unit cell is basically like a hexagonal prism, right? If you want to find the volume of a hexagonal prism, it's going to be the surface area at the top. So it's going to be A times the height h, right? So for a hexagonal prism, the volume is going to be surface area A times h. In this case, h is equals to c. Okay. Surface area for the top is basically going to be easy because we have triangles, right? Like you can divide this into triangles, basically. Like one triangle over there. So like if you look at this, you can divide this into 1 triangle, 2 triangle, 3 triangle, 4 triangle, 5 triangle, 6 triangles, right? 1, 2, 3, 4, 5, 6. And you know that from this to this is A. These are all equilateral triangles, so it's A over here, half base times height. And the height of an equilateral triangle is basically a squared, minus a over 2 a squared, like something like that. So basically the volume of A, so A is going to be 1/2 base times height times 6, because you have 6 triangles at the top. So 6 times 1/2 the base of an equilateral triangle is going to be A, multiplied by the height of an equilateral triangle. It's like what I said, guys. If you look at this, this is A over 2. So the height h is going to be the square root, using Pythagoras, the square root of a squared minus a over 2 squared. So it's going to be root 3 over 2a. So this is going to give you roughly 3 root 3 over 2a squared. And then the volume, so the total volume is now going to be equal to a times c, 3 root 3 over 2a squared times the value of c. I have it. The value of c is 2 root 6 over 3a. 2 root 6 over 3a. This is going to give you 3 root 2a cubed. So the atomic packing factor is going to be equal to pi a cubed, which is VA, divided by 3 root 2a cubed, which is VC. And this is going to give you 0.74, or 74% is basically made up of atoms for this unit cell. So that's basically the derivation for hexagonal. It's a little bit more trickier, but it's more fun.